All right, thanks, Phil. Just want to double check that you can see my screen and hear me.
Yeah, I can see your screen and hear you.
Very good. Thank you for the introduction. I just want to quickly start off by giving a big shout out and thanks to everybody on the QLCS research team, if you will, for making this work possible. There's lots of different expertise that each of them bring to the table, and I'm really thankful to have each of them helping out and making this work possible. So what I'm going to present today is basically just some initial results and conclusions from this ongoing work about QLCS Mesovortices. So far, we've looked at 127 Mesovortices. The map on the right is showing the location of all those different Mesovortices. 82 of them are tornadic, 45 are non-tornadic. I do want to point out that nothing here is peer-reviewed just yet. This is all kind of initial stuff. The analysis itself, I took a very operationally available approach where I'm just using cursor readout to look at the max values of these various signatures with each volume scan. And really the whole idea is to build upon some of the 3 ingredients method framework, especially the radar confidence builders and nudgers, and just try to fit Dual-Pol into that idea in a similar manner of maybe producing some more confidence builders or something along those lines. Feedback on this work is very much welcome since it's initial, and I'm always interested in feedback from forecasters on, is the direction of the work appropriate? Is the work relevant to problems that you might face while issuing warnings? Is there something that's missing? Is there something that could be added that would make the work more useful? So all of that is always welcomed at any point in time during this webinar, as well as after and just in general. So I'm going to jump right into the conclusions, and we're going to go through each one of these conclusions more in depth. But basically, there are several KDP signatures that look relatively useful when it comes to anticipating mesovortices and potentially their tornado potential as well. I'm really growing to like KDP as a radar variable, not only from downbursts that Phil mentioned, but also they seem to be relatively useful for QLCS events as well. ZDR columns and upper level reflectivity cores, a bit more mixed results there. And then we'll also talk about one non-Dual-Pol signature within spectrum width. So first up is I won't say I've called, but what is called a KDP drop. And it's basically just an area of low KDP behind the main convective line. And it's really a similar idea and similar location to a reflectivity drop that's within the 3 ingredients method framework. And so really this low KDP, it just kind of eats into the main convective line. You can really think about it like the rear inflow jet is descending and drying, and the precipitation is evaporating away. And so you get these lower values of KDP eaten to the line. Sometimes you even get a KDP line break. So there'll be a break in the higher KDP, just like you can sometimes see in reflectivity. This animation is showing one example, but I also wanted to show a few others as well that are static images. So this is the same example that the loop was showing, but basically here's the KDP drop behind the main convective line and those lower values of KDP. The animation was a nice, big, obvious one. They're not always quite so obvious. So here's an example of KDP drop that's a lot more subtle. You can see a subtle Z drop as well with this decrease in Z right behind the line. And then same thing with the KDP. It's like there's this little notch almost in the line, right where that KDP or the lower values of KDP are encroaching or eating into the line there. This is a zoomed in version. I did want to zoom out a little bit just to show that they can be relatively small. A nice small little notch, maybe even a little KDP line break right there. So one of the first things that we looked at was is there a preferred location where a mesovortex will develop related to this KDP drop? Because these KDP drops do precede mesovortex development. So very simply, we just kind of divided the KDP drop in half. So this would be the left side, this would be the right side, and we looked and saw where the mesovortices were located relative to that left and right side, and it's relative to storm motion. And we found that a pretty good majority, right around 73% or so, of the mesovortices formed on the left side of the KDP drop. Now, this particular example has both. So the strongest mesovortex did form on the left side of the KDP drop, but you can see there's also two other mesovortices that actually formed on the right side of the KDP drop. So it can happen. You can see about 13% of tornadic mesovortices form on the right side. It's just a little less common. You might also notice from this table that it's relatively unusual for there to be mesovortices that are not associated with a KDP drop. So about 94% of all the mesovortices that we looked at so far were preceded by one of these KDP drops. So sticking with KDP, next up will be the low and mid-level KDP cores. So we'll first look at mid-level KDP core. We've got an animation of one of those going on right now. It's just an area of higher KDP, greater than 1 degree per kilometer in general, that's at the elevation angle closest to, but below the environmental melting layer. So this is really similar to the downburst work that I've done, where we're not looking above the melting layer, but we're trying to look as close as we can to the melting layer and a little bit below it, where you can start to see maybe some melting hail that might be going on there, and really just trying to avoid any updraft effects that might be influencing it. Kind of want to focus on the downdraft, the KDP core, rather than the KDP column, which would be more associated with an updraft. I call these mid-level KDP cores, but it's just near the melting layer. And they do form either on the edges or within the rear inflow jet. And I would say the most common place would be on the edges of the rear inflow jet. In terms of the low-level KDP core, it's exactly the same idea as the mid-level, but I only looked at the 0.5 degree elevation angle. And the low-level KDP core is usually located pretty darn close to the mesovortex, as well as the KDP drop. So in this particular example, you can see the KDP drop really eating into the line there, and the KDP core forms right on the north side of that KDP drop. And then there are multiple mesovortices. You can actually see a couple of tornado debris signatures as well. So there's a lot going on with this example, but both of these tornadic mesovortices are pretty close to the low-level KDP core, as well as on the left side of this KDP drop. The KDP cores are useful because they are present with a pretty big majority of the mesovortices that we looked at. And they typically do develop before the mesovortex does, especially those mid-level KDP cores. They can develop usually 10 or more minutes before the mesovortex develops at the 0.5 degree elevation angle. The low-level KDP cores, that's a shorter bit of lead time, if you will. Sometimes they form at about the same time as the mesovortex, and then sometimes they form 7 or even a few minutes longer than that prior to mesovortex genesis. Another thing that I want to point out, and I'll probably mention this a couple times, is you might notice that these KDP cores are associated with both tornadic and non-tornadic mesovortices. So just like in the 3 ingredients method framework, a lot of those radar signatures are mesovortex precursors, not tornado precursors. And I think the same can be said about these dual-pol signatures, that since they're associated with both tornadic and non-tornadic mesovortices, it's a mesovortex precursor, not a tornado precursor. But of course, we want to know, will a mesovortex produce a tornado or not? And so that's where I think looking at the magnitude of the signatures can potentially be helpful. So looking at the low-level looking at KDP cores at the low levels on the left and then mid-levels on the right, we can see through these violin plots that there are differences between tornadic and non-tornadic mesovortices. So just to orient you to the violin plots, the width of the red is just showing the distribution. So the wider the red area is, the more observations there are at that particular value. And then I also overlaid the more traditional box and whisker plots on top of the violin plots, with this line right here being the median. So we do have statistically significant differences between the KDP core magnitudes of tornadic and non-tornadic mesovortices, with tornadic mesovortices being associated with much stronger KDP cores. And that is true at the low levels, or 0.5 degrees, as well as the mid levels, or basically near the melting layer. So I like KDP cores because they form, especially mid-level, form before the mesovortex develops, and potentially the magnitude of that core could give an idea of a mesovortex or a mesovortices tornado potential. This is a similar plot, but I broke it down based on EF rating, and it was interesting and kind of encouraging to see that there was this general upward trend. Granted, sample sizes are pretty small, but general upward trend in the magnitude of the KDP core as the EF scale rating increased. Now, there are not statistically significant differences between, say, EF0 and 1 tornadoes versus EF2 and EF3 tornadoes. This is actually a question that Vivek, who is helping out with this work, has asked a lot. You know, is there a way to differentiate between the EF0, EF1 tornadoes and the EF2, EF3 tornadoes? So while the KDP cores are a little bit stronger, the results were not statistically significant. Now, that being said, if you wanted to, say, look at non-tornadic mesovortices versus mesovortices that produced EF1 plus or even EF2 plus tornadoes, those differences would be even bigger than just the tornadic versus non-tornadic plot that I showed on the previous slide, since these KDP cores do get a little bit stronger as the EF rating increases. And of course, there are lots of caveats there with if a strong tornado is out in the middle of a field and doesn't damage anything, it's not actually an EF0 tornado, but you know, there are limitations to some of these particular things. And I ran into that with the downburst work as well, a lot with how strong actually is a downburst. Same thing can be said here, how strong actually is each mesovortex. So moving on to another dual pole signature is the ZDR column. This is a signature that's been identified for a long time in the research. It's really good for getting an idea of where an updraft is located, and can also give an idea of the relative magnitude of that updraft as well. So for this work, I looked at a lot of different aspects of the ZDR column. For example, I looked at CAPIs at different heights and measured the magnitude or the maximum value of the ZDR column on those CAPIs. I also looked at the height of the ZDR column and then the magnitude of ZDR at the top of the ZDR column as well. And this animation is just showing one of those ZDR columns, which is really just going to be an area of 1+ dB ZDR anywhere above the environmental melting layer. Now for ZDR columns, the table on the left shows that they do precede most mesovortices, about 70 to 75% of them. But unlike with the KDP cores, basically not seeing a difference between the magnitude of the ZDR column or the height of the ZDR column and whether a mesovortex is tornadic or not. So when we look at these plots, we can see that there is a lot of overlap between the two mesovortex types, tornadic and non-tornadic. In fact, the medians are pretty darn close to each other. So in this case, you couldn't pick out a value, let's say 3, and say, oh yeah, of course it's going to be tornadic, or of course it's going to be non-tornadic, because there's a lot of overlap. And something, so Keith has also helped out a lot. A question that he asked a long time ago was, well, you know, ZDR columns are going to be impacted by environmental characteristics like instability, as well as range from the radar, because your vertical resolution is worse the further out you go from the radar. So that can lead to issues in terms of measuring the true height of the ZDR column. So our question was, if we break this out based on instability and range, will we see any differences between tornadic and non-tornadic mesovortices? And so Keith helped out a lot with this work, especially on the environmental side. But what we found was it didn't make a difference. So when you account for range from the radar and instability, we still see lots and lots of overlap between the ZDR column characteristics between the tornadic and non-tornadic mesovortices. So definitely something important to look at. I was a little bit surprised by this, but I think my initial thoughts are, we know that a ZDR column is related to updraft magnitude, but to what degree? Is it a measure of, maybe the integrated updraft, the entire updraft? Is it a measure of the mid-level and upper-level updraft only? How much does a ZDR column tell us about low-level updraft strength, which I think is probably most important when it comes to mesovortex development, is the low-level updraft strength. And I don't think we know yet how connected a ZDR column is to the low-level updraft strength. And so perhaps what we're getting at is more of a overall storm intensity measurement when it comes to the ZDR column, rather than what is our mesovortex development potential like. That's just kind of my initial hypothesis right now. Moving on to -20C reflectivity cores. In previous research, the 50 dBz threshold has been very common to use, but I have found that it's not the best threshold for QLCSs. And in retrospect, this isn't particularly surprising, since a lot of these events were lower CAPE, those low CAPE, high shear situations, and the reflectivity core, or the updrafts and reflectivity cores, just aren't all that deep. So there were a majority of mesovortices were actually not accompanied by a 50+ dBz -20C reflectivity core. It's only about 40% were. So it's possible that if this threshold were changed, those numbers would get better. In fact, I think it would get better, if we did 30 or 40 dBz as a threshold. But I will say that there were quite a few events that basically just didn't have appreciable reflectivity at -20C. Now, in the events that we did have, the 40% of events that did have a strong -20C reflectivity core, we can see something similar to the ZDR column. This isn't surprising for the same reasons that I just tried to kind of think out loud about with the ZDR column, but we don't see much in the way of differences between the reflectivity core strength, so just the max value, between tornadic and non-tornadic mesovortices. And then the last signature that I'll talk about is not a dual pole signature, it's in spectrum width. We're calling it a low-level area of enhanced spectrum width, and that's a mouthful, and there's not a good acronym with that. So I'll be thinking about it, maybe a better, quote-unquote, better name for that. But this is just an area of enhanced spectrum width, typically about 7 meters per second or higher, that develops at the 0.5 degree elevation angle. And it is typically co-located with your mesovortex, which of course we would expect with the extra turbulence and then variability in the velocity measurements. We'd expect higher spectrum widths with your shear and rotation with those mesovortices. These do develop at about the same time as the mesovortex. Many mesovortices are associated with these spectrum width signatures. They just form at about the same time. So I can't really call it a precursor to mesovortex genesis because they develop at about the same time. Occasionally, you'll get one of these signatures to develop maybe 2 to 4 minutes before your mesovortex does, but for the most part, it's about the same time. Now, that being said, this low level, or this spectrum width signature would develop before the tornado does, just not before the mesovortex does. And once again, we can see that with the violin plots, we do have statistically significant differences between the magnitude of that spectrum width at 0.5 degrees for the tornadic and non-tornadic mesovortices, with tornadic mesovortices having stronger spectrum width or higher spectrum width than the non-tornadic mesovortices. So potentially this could be a diagnostic signature to give a hint at how strong the mesovortex might be, but not necessarily a precursor signature. And then a quick little bonus, mesovortex rotational velocity. So one measure of mesovortex strength is higher for tornadic mesovortices than non-tornadic mesovortices, and it is statistically significant in terms of the differences, with those tornadic mesovortices having stronger rotational velocities than the non-tornadic ones. This is not surprising, but it's nice to confirm an expected result, and that's in line with previous research. But once again, like spectrum width, rotational velocity is not going to be predictive, right? Like once the mesovortex is developed, it's too late to get lead time per se, but it could be a good diagnostic signature for how strong any given event might be. So just to summarize all of that up, I think there are potentially useful dual-pol signatures to be had when it comes to QLCS mesovortices, especially in KDP. Those mid-level KDP cores especially precede mesovortex genesis by 10 or more minutes, and they tend to be stronger for the tornadic mesovortices than the non-tornadic mesovortices. Low-level KDP cores are the same, they just precede mesovortex genesis by a lesser amount of time than the mid-level KDP cores do. The ZDR columns and upper level or -20C reflectivity cores might be a little less useful just because we didn't see differences between tornadic and non-tornadic mesovortices. But once again, we're trying to come at this from a 3 ingredients method framework. So it could be another confidence builder. If you have a nice strong ZDR column, at least you know that you've got a strong storm out there, a strong, probably mid-level updraft. And if you see some of these other signatures along with it, that could increase the confidence that maybe mesovortex genesis is imminent. And then that low-level area of enhanced spectrum width might be a better diagnostic signature than a precursor signature, similar to rotational velocity, just because those signatures show up at about the same time as your mesovortex is developing. And then this table, I basically showed little snippets of this throughout the whole presentation, but this table is just showing the prevalence of how common all of these different signatures are with tornadic and non-tornadic mesovortices. And so I can reiterate that tornadic and non-tornadic mesovortices are accompanied by these dual-pol signatures. So once again, they're mesovortex precursors, not tornado precursors, but the magnitude, especially when it comes to KDP cores, might give some confidence or some at least initial idea of how strong a certain mesovortex might be or what its tornado potential looks like. The QR code on the left will take you to what I'm calling an interactive presentation. It's basically a Google slide set where you can click around the different signatures, look at different maps, and kind of just explore this all on your own time if you wanted to. Or of course, you can email me and I can send the link to that Google slide set directly. But that is the extent of the presentation. Thank you all for your time and attention. And if there are any questions or comments, feedback, I am definitely really interested in hearing your all's thoughts about this early work. So thanks again.